Welcome to today's webinar brought to you by Hazelcast and Synadia. I'm Stephen Fegg, Director of Database Trends and Applications and Unisphere Research. I will be your host for today's broadcast. Our presentation today is titled Building and Managing a High-Performance Microservices Architecture. Before we begin, I want to explain how you can be a part of this broadcast. There will be a question and answer session. If you have a question during the presentation, just type it into the question box provided and click on the submit button. We're going to try to get to as many questions as possible later. Plus, all viewers today will be entered for a chance to win a $100 Amazon gift card just for participating. Now, to introduce our speakers for today, we have Randy May, Principal Architect at Hazelcast, and Jeremy Saenz, Director of Developer Experience at Synadia. I'm going to pass the event over to Randy to get us started. Welcome to the broadcast, Randy.
Hi there. Thank you, Stephen. Excited to be here. As I mentioned, or as you mentioned, my name is Randy May. I'm a principal architect at Hazelcast, and my background is all basically working with our customers and enterprise customers to using either in-memory data grid technology or event processing technology to solve their business problems. So, I think this is a great topic. So I'll go ahead and get started. We're only going to have a few minutes, so my short amount of time. So I just want to make my thesis clear here. So when building an event-driven microservice architecture, it's very important, or it's very important to consider event-driven architecture as opposed to your typical kind of request response type of architecture. And so the first thing I want to do is do a kind of a compare and contrast of the two architectures. And then the second thing is, given that you're going to implement an event-driven architecture, how to do it. And I would like to argue that using a stream processing technology, something that's purpose-built to process event streams, is something that you really want to do. And so those are the two topics I want to generally go through. And of course, it's going to be very fast, but hopefully we'll be able to get into it in more detail in the Q&A section. So with that, let's kind of start the compare and contrast. So I'm going to use the retail example because everybody knows that domain. It's very familiar. So let's just start off with a online retail website that has an order service, typical web service, maybe hosted by Spring Boot. And then that order service needs to call several other services to get the job done. So it needs to accept payment, it needs to potentially manipulate the inventory, and it needs to initiate shipment. All right, so we can just start right there and consider a few things from three perspectives. So first, resilience. So these microservices calling each other is typical. What happens if I'm accepting an order on the website and the payment has happened and the call to the inventory has happened, and then the shipping service is not available? So do I return an error from that order service and not take the order? That's bad. But on the other hand, do I actually go ahead and take the order? In that case, how do I make sure that it's going to get shipped? Now I need an extra mechanism to kind of capture the fact that the order was placed, but the shipment didn't happen. And we're already leaning toward event-driven, as you can just with that. And then let's also look at coupling. I think this is not bad, but clearly the order service has to know about the payment service, the inventory service, and the shipping service. And and it's got to, for example, have stubs for it in the test environment, so that, and anytime one of those changes, it is possible that they impact the order service. And let's suppose we wanted to add like a notification service to the picture. Now the order service has to be modified to call the notification service, and the shipping service has to be modified also. So like when the when the item actually ships, we'd like to tell the customer, that would be what the shipping service would do. And you would have to update both of these services. So now, and then the last thing is from a performance perspective. So as long as there's no blocking and I'm using all the CPU that I have available to me to do business processing, everything's fine. But with typical web service calls, like a REST call or something like that, it's pretty normal for some of these calls to be made in a blocking manner, and that can be very destructive of throughput. So again, this is something that is, the async aspect of this is just something that you absolutely can do in a traditional web service, but it's built into the platform, so your developers don't have to worry about it if you're built into the architecture if you're doing event driven. So that's kind of the retail example from a few different points of view, built using sort of traditional web services. Now let's flip it around a little bit and look at how, see how this would look if we're doing event-driven architecture. So, and just to show that, it doesn't have to be all or nothing. I've got a synchronous connection between the order service and payments. There's third parties. There's some things that it makes sense to do synchronously. So, and I think authorizing the payment is one. So once we authorize the payment, then the order services job is just to capture the facts of the order and publish them to an order topic, and then it's done. And then the inventory service can pick up on that order topic and do its job. Same with the shipping service. It can pick up on that order topic and do its job. So now let's go back over the same list of concerns. So from a resilience point of view, this is the problem that we discussed earlier is solved, right? As soon as the order service writes that order to the topic, it's persistent, and if the shipping service isn't up right away, or if you're upgrading it right at the moment, then that's fine. As soon as it comes back up, it'll finish doing the job. So that buffering and resilience is built in, and it also makes it easier for you to do upgrades. From a coupling point of view, I think this is one of the more interesting aspects of event-driven architecture. So from a coupling point of view, notice that the order service actually no longer knows even who's using it, right? Or who's consuming the order downstream. So changes in the inventory service and the shipping service can't affect the order service at all. And if I want to add another service, like the notification service, this time, the order service doesn't have to change at all. I'm free to add new services that consume that order at any time. So coupling is looser in this event-driven model, which is nice. It lends itself to basically higher agility and faster time to market. And then lastly, performance in event-driven architecture is just async, just by its nature, asynchronous and non-blocking from end to end. So generally, it's also going to scale well, scale better. So they're both running the same business logic, but one is just going to, as a matter of architecture, invoke everything asynchronously. So there's advantages there. So that's just a very quick argument for why event-driven is an important architecture for microservices. And so then the next thing I'd like to talk about is, well, how do you actually implement this? And there's different ways, and I'd like to compare some of the different approaches. So first approach is just a pretty natural extension of the kind of a traditional, say, Spring Boot based microservice approach. Just leave all the business logic in app servers. And it's easy to write a web service, or it's easy to write a service that consumes events rather than listens to REST calls. And one thing I'd like to point out is that in this architecture, in all three of these architectures, you're almost always going to need some kind of fast data layer, cache, whatever you want to call it, because the event coming in if it's an order, I need to look up information about the customer, say the customer's address, right? That's not in the order. I've got to look it up. And going back to a database every time you process an order is probably, especially if it's a, internet facing website, that's probably not feasible. So you end up introducing this fast data layer into your architecture, and that's the function of that. Okay, so that's variant one. Now variant two is to use a stream processor for processing messages rather than using app servers. And again, this is a big topic, and hopefully we'll get into it in the Q&A. But stream processors can do some things that app servers that are much harder to do with just a traditional app server based microservice. And some of those things are anything that requires like state over time. Like I'd like to do some aggregations, or I'd like to detect a pattern, like when a certain temperature reading goes over a certain threshold, emit an event that's an alert, but don't do it every time. Do it only the first time. So there are a lot of use cases that when you start thinking about it require some state, and event processors are very good at that. And so that's the second option here. Basically use a stream processor in your stack for processing messages, and use an app server for processing requests. Now, one little adjustment we can make that will make our stack simpler is let's just consider an HTTP request as an event. And if we do that, so that's the third option. If we do that, we can put all the business logic into the same platform, into this stream processing platform. And we just need something, an API gateway, like you could certainly do this with Kong, or that accepts HTTP connections and turns them into events. And this results in a simpler stack. So, and then the last thing, and this is where we're going to get a little bit more Hazelcast specific, but I think it's really important, is that these three vertical boxes here, this is kind of how the industry has evolved into categories, but it's not the only way to write software. So Hazelcast for more than 5 years has actually been combining a stream processor with fast data, and it does it in a smart way. Like if you think about again, going back to the example of processing an order and needing to access the customer's information, if you combine these two, then it's possible to process that order on the node where the customer's information actually already lives. That's very powerful. And that's something that Hazelcast does. So that yields, the absolute lowest latency. May not be as important in retail, but if it's more like real-time recommendations or something like that, or even real-time machine monitoring and control, then that latency makes a big difference. Okay, so I know that was fast, but that's what I'd like to say about building an event-driven, building a high-performance microservice architecture. First, consider event-driven, and second, have a look at stream processors. So now, for the last couple of minutes, I would just like to show you an example that's running in Hazelcast. So this is a little schematic of the example, and basically, we've got simulated factory emitting events. They're like machine temperature events. And then we have two services, and these are implemented as Hazelcast pipelines. Got two services, one that's summarizing the events. What's the average temperature over the past 5 minutes? And then one, and it drops those into a map that's in Hazelcast. And then one that's retrieving the status and also providing some like it'll categorize it. 100 degrees, is that normal or not? Is that red, green, or blue, red, green, or yellow, that kind of thing. So with that, let me share my screen real quick, and then I'll pass it off to Jeremy. Okay, So here is the Hazelcast dashboard, and you can see what I have running here is a cluster of 2 members. And if you kind of look down the left-hand side here, you can get an idea for what is in the platform. So there's a storage aspect, and the most popular storage choice is maps, just a key value store. It's very useful. And then there's jobs. So let's look at let's quickly look at these jobs. So we've got 2 jobs running right now. Just like I said, one is doing the aggregation and one is handling request responses. And I've got something that's running in the background submitting web service requests. So one's handling request responses and one is doing, like I said, doing the aggregation. And so I'm going to click into this one, and you can see when you write one of these, you just write a series of steps, and then Hazelcast distributes those steps over the whole cluster. And then we can see exactly what's going on at each step. So for example, I just clicked on that one particular step, and you can see that there's actually, in this case, looks like 10 different processors running on the cluster, and they're all processing a portion of the workload. And then just to wrap it up, the maps are listed here, and in most cases, you can actually look at the data with SQL. So we've got a machine status summary map. That's the service that does the aggregation is writing into that map. So if I click on that, you can actually see that that map is being constantly updated. And that's because that's what the summary service is doing. The summary service is digesting events from Red Panda and summarizing, and then there's a request response. And so let's just look at one of the responses coming back. So basically, we use a map for the input of the web service and a map for the output. So if we look at, let's look at the response, just one particular response. Oh. Forgot to set that one up. There it is. Okay, there we go. Okay, and we can see that these responses are basically coming back with the serial number. Here's the average temperature. Here's the warning. Here's where it's been enhanced. So the warning level is here, or the critical hit is here, and so the status of this one is green, and like that. So anyway, that's just a very quick tour of the Hazelcast platform for implementing web services and also event-based services. Okay, so I will stop sharing my screen, and we can pass it on to Jeremy. If you'd like to connect, join the Hazelcast community or anything, you can use those codes there to either join the community, either Slack or Twitch. All right, and I think that's it for me.
Thank you very much, Randy. Okay, Jeremy, welcome to the broadcast.
All right. Hi, everybody. Thanks for having me on board. Like I said, or like I was introduced, my name's Jeremy. I'm a software engineer and director of developer experience here at Synadia. And I'm here to talk to you about how to build adaptive microservices using a technology called NATS. Now, NATS is a huge technology, so I'm not going to be able to cover the full breadth of things, but I'll try to kind of fill in the blanks of like where you might want to kind of, check things out a little bit more. But it's a super fun technology, and there's a lot of different ways that NATS kind of approaches some of these common problems that we have as developers, especially when we're looking into scale, either global scale or going out to the edge, going multi-cloud, or just wrestling with like distribution inside of your organization through like, microservice architectures and things like that. So I'm mostly going to be focusing on the microservices side today, and we'll have a lot of fun. We're going to do some fun demos as well. So at Synadia, one of the things that we talk a lot about is this idea of rethinking how things connect to each other. And one of the reasons that one of the things that's really driving this discourse for us and a lot of other organizations that we work with is things like multi-cloud and edge computing. It's just driving a huge transformation inside of organizations. And I think at the core of it, there's really this like sense of distribution, whether you're distributing your applications or your data more geographically, like going multi-cloud or going out to the edge, or you're distributing your data and your applications more organizationally. You're spinning up new teams and you're trying to figure out how to wrestle with this idea of scale with both people and with actual volume in terms of your business. And so, we think at the heart of it, rethinking some of our common core assumptions about how things connect to each other, how applications and data connect to each other, is really at the heart of what can bring a huge advantage to a lot of organizations today. And when I talk about kind of like these core assumptions that we're rethinking, a lot of it has to do with stuff that just feels like the bread and butter of how stuff should communicate. Things like, oh, we should be using DNS and IPs and talk one-to-one between all of our services. And that we should, do kind of a poll-based request-reply semantic where somebody might be calling an HTTP server and getting a response back synchronously. We also kind of have built, especially with the cloud, this idea that like perimeter-based security is like the most, manageable and the de facto standard, where we just put everything inside of a VPC in the cloud and put up our walls and say, cool, we're good, we're secure now. And there's a lot of location-dependent backends. We might just have one, SQL server somewhere in some region that is serving all of our requests. And sure, it might be over provisioned and we might get good performance out of it, but we're still struggling with latency, especially when we want to spread out more globally. And at its core, I believe that these things are just a lot of layers built on top of this like assumed one-to-one communication, oftentimes with things like HTTP, which remember was designed for a hypermedia use case for browsers to interact with web servers. And for some reason, we also adopted a lot of those same semantics when it came to how our microservices communicate with each other. And today I'm going to kind of, show you guys maybe an alternate way to think about some of these things and ways that organizations today are adopting these to just be able to run a lot faster, to be more adaptive, and to overcome a lot of the challenges that typically come with the territory of adopting microservices inside of an organization. So NATS is an open source, high performance messaging system and a connective fabric. And the reason I'm using the term connective fabric is you're going to see is NATS not only just facilitates communication, but it really is the broker for everything around that application lifecycle to the point where it's very easy to kind of plug in and observe, for instance, everything that's going on inside of that communication fabric. And so I'm going to kind of introduce you a little bit to NATS. We'll show some demos, and I'll talk about kind of how NATS works really well for things like microservices. But at its core, NATS is really here to simplify the number of technologies that you want to use to have your services communicate. And it's also there to empower you for scale. So building systems that are globally available, maybe they're multi-cloud or multi-geo or out to the edge. And most importantly, they're highly adaptive to change and scale. One of the challenges with microservices, and I'm sure we'll get to this in the Q&A, is the inability to be adaptive is really what slows down teams from being able to adopt microservice architectures well. And at its core, this is one of the things that NATS does really well, is it allows you that room, that breathing room and that space to be able to express and slowly move toward a better microservice architecture without chaos and anarchy reigning. And so one of the things that NATS does to kind of address some of these problems that I outlined earlier is that we have location independent addressing, meaning all the communication goes through a series of NATS servers, meaning all you need to know is the IP address or the DNS domain name of the NATS server. And then everything else can now communicate with each other without having to go through DNS lookups or IP addresses or anything like that, which makes for a really good story around microservices and discovery. NATS is also quite naturally end-to-end communication based, meaning I don't need to know the address of something to talk to it. I just need to know what I want to talk about, what kind of topic or subject in our case, and then I can start having conversations with everybody who's interested. It's also push and pull based, meaning we don't necessarily always have to use a request response pattern, but we can go fully asynchronous with pub sub, fan in and fan out patterns, as well as persistence patterns, multiple different types of persistence patterns with a technology called NATS Jetstream. It's also decentralized in terms of security and authentication and authorization. And I won't be able to go too deep into this model, but it's a super interesting topic, especially when you start going outside of your like four walls of security. You have to really start approaching things from some like zero trust kind of constructs where you can't really fully trust any party. And there's some really interesting developments in that space. And NATS is also very supportive of this model. Like I said, we have a very intelligent persistence layer in case you want to be able to kind of do stream processing as was covered before, or any other kind of models like key value storage and object store. All of that can be expressed in NATS Jetstream as well. And really, NATS was built from the ground up to be these like servers that you can Lego brick together into any sort of arbitrary topology. And what we see a lot of organizations do is use this to kind of like have a fully global scale and presence where you can deploy these NAT servers really anywhere at the very edge, close to your customers or in multiple data centers. And it facilitates that communication without having to punch through all these firewalls or go through proxy after proxy after proxy to be able to communicate with a service that lives somewhere. It's all just kind of transparently handled for you. And NATS is intelligent enough to be able to make that performant. And so that's kind of the high level overview of NATS. More practically, NATS architecture is a simple client server model. You go build clients that connect to NATS servers, and those NATS servers facilitate all the communication between those two. The cool thing about the NATS server is that it's small. It's built in Go. It's really easy to use, really easy to spin up, single binary that can be deployed in many OSs, many environments. We even get NATS servers running on like a Raspberry Pi 02. So not quite microcontrollers, but like very low power single board computers can run a NATS server. And so they can also, like I said, be Lego bricked into all kinds of really fun topologies. I wish I could get into that a little bit more, but I do have some video content on that if you're interested, and I'll have some links at the end of this talk. As far as the client side, NATS supports 40 different kind of client library implementations from Java, C#, Go, Rust, anything you can kind of think of in terms of popular languages. It likely has a NATS client library, and they're all idiomatically designed for the particular language, which is a monumental effort on our part, but we think it works really, really well to try to, respect the idioms of the various different languages. And it has first-class support for microservices, which I'm going to be showing today. Kind of to tease some other parts of the architecture apart, we have Core NATS, which is what I'm going to be showcasing today, which is kind of a fire and forget message publishing pattern, supports request reply, things like that. And then we have Jetstream, which is kind of your ability to have some sort of temporal decoupling, meaning I can publish a message, NATS saves it somewhere. We have things from, replication, key value stores, object stores, a very, very flexible way to be able to kind of save and shuffle around your data and make sure that the data is delivered consistently. So we often see companies using NATS Jetstream to replace things like Kafka or Redis or RabbitMQ, because NATS can express all of those patterns very, very well in a single system with a single security model. And that's a really, really compelling offer for a lot of organizations that are trying to settle on microservice architectures. So what's Core NATS? Well, Core NATS, it's fire and forget message publishing, meaning we're not saving messages for you. NATS is really just brokering communication between two clients. And the reason we have this is because it's kind of the foundation for all of the other features. And quite often, especially when you're working in a synchronous architecture, you might not need the persistence layer. You just want to be able to broker communications in a location transparent way. So it's easy for things to connect and talk to each other without having to have all of these tools like service discovery and schema registries and things like that. And it's very, very fast, which I'll show in a second. And so things like request reply, publish subscribe, fan in, fan out, scatter gather, and free load balancing, which is super cool. That all comes with Core NATS, and it's super, super easy to play with and learn. Jetstream, I'm not going to completely cover, but I went over some of the basics. It's a distributed persistence layer, it's multi-tenant, it's fast, and it's really easy to persist messages in various ways. And here's all kind of the patterns that Jetstream supports. So I know I don't have a ton of time, so I want to get into a quick demo of NATS, and then we'll talk a little bit about microservices, and then we'll field some questions together. So I'm going to go ahead and share my screen. Now, the fun part about NATS is, although we have these 40 different client library implementations, one of my favorite things is that we actually have a NATS CLI, it's called the NATS command. And basically everything that you could do inside a client library, you could just do in the shell as well. So like things like prototyping and proof of concepts, like honestly, it takes folks what proof of concepts that would normally take weeks or months for some teams are just taking hours or days, mainly because it's so easy to play with NATS. So I encourage anybody who's interested in kind of playing around with this to go ahead and, like, after this talk, download the NATS server, download the NATS CLI, and just start playing with stuff. All these commands that I'm running, I'm not doing anything special. I'm doing it all from scratch, and you'll be able to see how fun and easy it is to play with. So I'm going to fire up a NATS server just with the NATS server command. And that's how easy it is to fire up a NATS server. Easy, single binary, very small. Now I'm going to start running the NATS CLI. And like I said, NATS has support for pub sub at its very core. That's kind of a core fundamental. So I could say, NATS sub hello.star. Now this star is kind of a wild card. So anything that's like hello dot whatever is going to be captured by this subscription. And then I can, do anything I want with it. So now I could say NATS pub. And I'm going to just say, hello, Jeremy. Hi there. Now, NATS is payload agnostic. So I'm just passing it a string here, but you could pass in JSON, BSON, whatever you really want to with that. So I could publish that message and you could see that it's received, which is great. That's super simple. I could even up the count to like 1,000. You can see I just published 1,000 messages very, very quickly here. NATS, like I said, is super performant. So I could even run the NATS command comes with a built-in benchmarking tool, which is also super great for proof of concepts and for trying to kind of figure out what are the upper limits or bounds of your particular system. And so I can publish 10 million messages on that NATS server that I just fired up, and we'll see how it goes. So in this particular instance, which by the way is a development build of the server, I'm clocking at about 4.2 million messages a second, which is really good. It's a lot of room to be able to do things. And that's just on one server. It's not counting partitions or clusters or anything like that. So that's pretty neat. But one of the really great things that enables microservices inside of NATS is this idea of the request reply pattern, where I could say NATS reply, and I can have something listen, and I'm going to just tell the NATS CLI to echo whatever it receives. But this is really the bread and butter of what microservices are. It's just a series of kind of endpoints or replies to particular subjects. And I could say NATS request, and I can make a request over to that particular echo, that particular hello dot Jeremy endpoint, and it will be received. Now, one of the other neat things about this whole pattern is I can get load balancing for free. So if I fire up another one of these replies, I can then start making a request, and it's going to randomly distribute the load between the two of those services. So they could spin up, they could spin down. We can, bring all this elasticity without having to consult or talk to a load balancer. NATS is just automatically doing that for you because it has all of that information available. It knows who's subscribed, who's interested, and even in a very distributed architecture, NATS will be intelligent about being able to route to the closest particular responder and also, randomly distribute it between all of its peers. So there's a lot of really cool things going on, which would take a lot of kit, it would take a lot of infrastructure to be able to do, and it's just all kind of here with NATS with no configuration, just kind of natural ergonomic results there. And so that's kind of a high level overview of core NATS. There's so much more I could cover, but I want to jump back in real quick to the slides to talk about microservices and then close with like one more demo. So I'm going to jump back in to the NATS micro library. So NATS micro is kind of a subset of the NATS kind of core client libraries that adds a microservice kind of a frameworkiness to NATS and uses all kind of the core NATS features to be able to express this. So this is really cool because it makes services that are like automatically discoverable, they're observable, and they're nomadic. And I'll tell you what that means kind of in a sec. But what do we need for microservice architectures? There's like a laundry list of things that are just like table stakes for like good microservice architectures. You need something to do service discovery and load balancing between all the servers, like we just talked about. Something to handle logging and monitoring, observability, authentication, authorization. We need API gateways to be able to capture things on the outside and convert them to the right format. And then we need configuration management for that stuff and maybe some sort of data store. And so like that ends up being a lot of technologies to wrangle. And a lot of organizations are struggling with all of that complexity. And one of the great things about NATS is we can solve all of these things with just like one technology. And you don't have to solve all of these things with NATS. Some people have their own preferences for stuff, but NATS handles a lot of this just out of the box. And so it can really help jumpstart a microservices adoption inside of your organization where you just have all of these things in one place. So today I'm going to cover like what does it look like to do automatic discovery, load balancing, observability, and even kind of this idea of an API gateway. So let's jump back in to the demo, and I'll kind of show you a little bit about the NATS micro library, and then we can do some Q&A. So we have a NATS micro command inside of NATS that allows us to do all kinds of fun stuff there. But really what the NATS micro command is it's kind of a reactive way to be able to monitor and get details on microservices, whether they exist, how to call them, how many of them are there, and even kind of monitoring and observability and logging around them. And so, and this is all just out of the box, part of like a client-side implementation. The server doesn't really know much about it. It's all just kind of conventional under the hood, which is actually really, really fascinating. But I could, create a new little microservice very easily by just saying NATS microserve. And this is just kind of as an example. And I'm just going to call this Echo. And so this created an Echo service with one endpoint called Echo. And I can actually now call that service by just saying NATS request echo.echo. And I'm just going to pass in, hey there. And that's going to respond with an echo of, hey there. And so you can see I'm now calling that service, which is great. But the other really cool thing about this now is if I go over to this tab, it's going to say, if I go over to this tab, NATS micro list, you could see that it knows about this Echo service. It knows what version it is. It has an ID that's assigned to that particular service. So if I go ahead and fire up like another one of these, NATS micro serve Echo, you can see that there will be like 2 of them now, which is awesome. And then we can also observe statistics on each of these. Now, Echo is kind of a, not as interesting kind of type of microservice. So let's actually go ahead and I'm going to jump into a demo where I've written a calculator service. And that calculator service does simple things. It does add, subtract, multiply, divide. Now, I've written this in Go. If you're not familiar with Go, don't worry. It's pretty easy to grok some of this. But this is just a showcase, that it's actually really easy to just like add and decorate this microservice. It's like, I don't know, 100 lines and goes kind of verbose. So like it's really not all that bad to write a simple microservice that does all of these things and gives you all of the information that you need. So I'm going to go ahead and fire this up. I'm going to say go run this thing, and I'll actually fire up another one as well, just so we have 2 instances of it. So I go back to NATS micro list, and you can see I have 2 calc services, 2 instances of it. So they're going to be load balanced between the 2 of them. And when I go over here, you could also see that we get statistics on all of these. Now, I'm not doing this in the CLI, but this is all just like JSON responses. So you could easily build tooling around this. I know plenty of community members have. But I could actually just start, interacting with this in interesting ways. I can say NATS micro info for my calc service. And it will tell me interesting things like here's all the endpoints that there are. Here's some descriptions of them. Here's some schema for the request and response. So now I know that it needs a JSON object that's, A and B for each of these endpoints. And so you get like automatic service discovery, automatic documentation kind of out of the box. So I can easily just say, okay, I need a JSON object where, A is 1 and B is 2. Okay, that looks good. Now I can say NATS request calc dot add, and it gave me 3. I could say subtract, and it gave me -1, which is correct. Multiply, great, gave me 2. And so I can now start interacting with this service and playing with it and integrating it into my application. And this is all, available to me. Works really, really well for organizations. So that's a high level overview of Nats Micro. I know I went really, really quickly, but hopefully you're able to see some of the power of this. And the last thing I want to say is I haven't been able to go over it, but all of these kind of subjects or topics that I'm interacting with, all of these can be very finely grained, locked down from an authentication and authorization purpose. And so you have one sort of like single security model that works really, really well, is decentralized, has zero trust constructs for being able to kind of lock all of these down and interact with them in a multi-tenant fashion. And so I wish I had more time to go over all of the cool multi-tenancy of all of this, but we'll have to save that for another time. But that's the high-level overview of how Nats Micro can help organizations with adopting microservices. If you guys are interested in learning more, you can go to Synadia.com, and we have a resources section where you can look at screencasts, and I go over tons of different topics covering, Jetstream or microservices or topologies, infrastructure, all of that, how to really use Nats to kind of redefine how a lot of the traditional architectures work. Nats is also, like I said, completely open source. You get everything. We're not an open core model. So everything I showed here is not put behind a paywall. But if you're interested in working, with some of Synadia's products, we work on really great tooling for operating Nats as well as hosting Nats. We also have a fully hosted version of Nats that's completely global that you can sign up for called Synadia Cloud. So if you're interested, feel free to visit any of those links. But that's all I have to talk about with Nats. So thank you.
Awesome. Thanks so much, Jeremy. Okay, at this point in time, we're going to dive into our group discussion. So I've got some questions for Randy and Jeremy. First question, and Randy, I'm going to let you go first. What are some key lessons you can share that IT leaders and teams should know about before diving in?
Before diving into microservices?
That's correct.
I think that I think it's important to basically, I've seen a lot of like whiteboard diagrams of this is how we want to end up, and they take the business or the section of the business that they're refactoring, and typically it's pretty easy to go ahead and plot out your microservices and decide what your services will be. But what I see gets neglected a lot is, there's very, very rarely do you have a greenfield effort where there aren't any existing systems, and you never can just stop. You can never just stop and cut over. So having the end goal in mind, the end blueprint is one thing, but you also have to actually plot a path. And so I would say, be prepared to pay a lot of attention to that. I think that's in a lot of ways even harder. Like, we'll convert this one first, and the fact that we're now moving the authoritative source of this data to a different place. How are we going to make sure that everybody that was using it can still get it? Maybe we'll create an event stream to do that. Things like that. So plotting the trajectory to your end course is really important.
Understood. Jeremy, any thoughts on key lessons you can share with the audience?
Yeah, I got to agree with Randy here in the sense of I don't think kind of big bang, switch over, lift and shift projects, work very often. They rarely ever work out. And so I would recommend that, creating a spirit of iteration, especially in the brownfield space, and adaptability, because you're not going to get it right the first time. Nobody ever does. And that's okay. Like, don't feel shame about that. The reality is you're trying to build an airplane while it's flying. So the only way you really can approach that is to optimize for adaptability, to iterate. And like Randy mentioned, as you're plotting that course, to be able to consider how can we get progress, while also keeping keeping the plane in the air, so to say, that is a challenge in and of itself. It involves knowing how your organization works at a very deep level. It involves knowing the technology and how all of it works at a very deep level. Being able to kind of piecemeal, take things little wins one at a time, I think is a really important kind of mindset to have.
I love the plane analogy. All right, moving on to our next question. Randy, is the rise of IoT and edge computing impacting how organizations are approaching software development as well as data storage and processing?
Yeah, I absolutely think so. There's a couple of challenges that come with IoT, typically come with IoT. One is just data volume, right? The data volume could be huge. And it might be like if you're talking about very fine-grained sensor data, it could even be thousands of samples per second. And so a couple of things. One is you may actually need something to pre-process those events and respond at the edge. And especially if you're doing something like you're trying to preventive maintenance, or you're trying to monitor and shut down a machine before it does fail, something like that. The other thing about the edge is you often have intermittent connectivity or poor connectivity. It's running over cellular, right? And you may not have it. So if you're relying on something central to make a decision to shut down that machine, well, you can't do that. You may need to push smarts and kind of data summarization functionality out to the edge.
Understood.
Yeah, I'm right in line there with Randy in terms of what I often like to say is what worked for cloud won't work for edge. And so if you're an organization that at all has even its eyes set on distributing your applications or your data more out towards the edge, whatever the edge might mean to you. I mean, for a lot of our the companies that we work for, it's often factory floors or folks that work in energy or transportations. We have NATs inside of electric vehicles and inside of trains and on oil rigs, and they all have some similar but very distinct problems that you really don't get when you're working inside of a single cloud provider. And so you have to kind of function very differently, I'd say. And so I think IoT and edge computing is obviously trending a ton right now from a competitive standpoint, but I think it's going to start becoming a de facto standard for a lot of organizations that need that kind of distribution model and need to go beyond the cloud. And it requires a different way of thinking. So anything from intermittent connectivity to being able to bring compute and processing closer, to Randy's point, sensor data and factory floors like produce an immense amount of data. It's naive to think that you could just push all of that to the cloud. So you have to be able to kind of localize the decision making, like what thing is making the decision and where, to be able to kind of help synthesize data and make better decisions overall. And that's one place that I think NATS as a technology really excels, is because you can really have that whole thing, that whole process facilitated by NATS.
Understood. Another big trend is something we're talking about quite a bit this year as well as last. And Jeremy, I'll let you go first. AI. Do you see microservices and AI converging in any areas? And if so, what are some of the interesting developments?
Yeah, I mean, there's a lot of developments in AI from, RAG, which is essentially like a augmentation of, various inferences related to large language models. But even, in more like traditional AI applications, like, image recognition, object detection, that's happening kind of and being deployed out into the real world today, whether it's traffic cameras, smart cities, being able to make decisions, in terms of energy, charging stations. Like I said, trying to bring the combination of edge and AI is actually a really fascinating crossover, because that idea of that I talked about of localizing decision making, that decision making is often being deferred to something that is AI driven in some way, shape, or form. And so the AI inference happening at the edge is interesting, and also being able to collect whatever data is happening at the edge and push that over to the learning side of AI that is usually happening in the cloud with a bunch of GPUs. But being able to get all of that stuff packaged up and sent over in an efficient way is also a challenge. So I think there's some interesting intersection happening between the edge and AI that I think a lot of organizations are still struggling to figure out.
Understood. Randy, what are your viewpoints on this?
Yeah, I think that much the same. I think that I think we're there. So I've definitely worked with customers who use microservices to basically to collect up all the features, that are inputs to their models. So just kind of talking just about classical ML, whether it's like scoring a credit card for fraud, likelihood of fraud, things like that. So yeah, I'm already seeing microservices being used to collect up the features that are input to the model, and in some cases, microservices being used to actually run the scoring engine, because having a model in Python that runs in Jupyter Notebook is one thing, but now I need to operationalize it. That's where microservices come in. I can't run just one. I need some way of scaling out that scoring model, different. There are different frameworks and microservice frameworks that help you do that. Hazelcast is that's something that Hazelcast does well as well. But yeah, I think it's already. What I've seen is it's already being done, at least for traditional ML.
Got it. Randy, can you expand on why you see a non-blocking architecture as important for high throughput systems?
Absolutely. So I've worked with a lot of customers on performance issues, and one category of issue is the code is inefficient or whatever. That's actually a little bit of a simpler category, but the one I actually see more commonly and that's more difficult to resolve is the system has a throughput ceiling, but it's still got plenty of CPU. We can't, it doesn't, there's plenty of CPU. Why isn't it going faster? And a lot of times it's because of synchronous or blocking interactions between components of the system. So it doesn't take too many, especially as you chain them together, it doesn't take too many before basically all your threads are just sitting there waiting for something else to happen. And so non-blocking architecture says don't ever wait. Don't ever wait. And that's key to being able to use your CPUs to do your workload.
Jeremy, any thoughts you'd like to add to that?
Yeah, I think I'd like to add, totally agreed with performance. I think the other aspect that a non-blocking architecture typically brings is just a different way. It kind of is a forcing function for a different way of thinking with how a lot of the teams interact and create contracts with one another, to the point where it naturally offers a lot more resilience. If all the teams are kind of thinking synchronously, you kind of get into that trap of where you've maybe seen a very disastrous microservice architecture where you have this one, REST call or request happening on the web front end that then makes hundreds of microservice requests, all kind of synchronous or aggregated, and it's just a performance mess. Whereas being able to approach it from a more asynchronous point of view, it does require a whole end-to-end kind of rethinking from the UX perspective on the web front end, but it does offer a lot more resiliency where teams are a bit more protective of how they think about retrieving data and knowing that like faults can happen at any time, or data could be missing in very many ways at different stages, versus just like a synchronous request taking a long time or timing out or failing. And so the faults and failure kind of get exposed a bit differently in asynchronous architectures. It is different and it has its own set of problems and learning curves, but I think it makes for an overall better experience the more distributed your team and applications are.
New question, Jeremy, from a developer perspective, is there a difference between writing code for a stream processor and traditional service code?
Yeah, that's a great question. I'd say in general, yes, but I see them as two different expressions of patterns, and I think it's good to call out like a stream processor versus microservice. And I'm a huge advocate of being able to mix those patterns into architecture and to kind of use the right tools for the job. Sometimes you want a request reply kind of synchronous, how we understand a lot of how microservices communicate. And then in a lot of other ways, you might want something to just be reactive to a set of events. In other circumstances, I know some people really get into like an event sourcing style architecture where you have some log that is the representation of the truth happening in actual kind of, a transaction like way. And everybody else is responsible for rebuilding a projection of the truth that is suitable for their application. So I like the idea of being able to mix a lot of those architectures and use the right tool for the job for that. And because in reality, like you have a lot of those patterns expressed anyway. So I think there's a difference in how you write them. But I also want to caveat that by saying that you should be mixing and matching, those different patterns, even inside of like accomplishing a simple task. So,
understood. Randy, what are you seeing amongst your customers?
Yeah, well, there's definitely a difference. I think Jeremy did a good job of covering it, but just to, if you're a Java developer, you can think of it as the differences. Stream processors take code that looks a lot like actually like Java streams, right? You just kind of are building this graph of steps, and each step, might be a accumulate step, or it might be a map step, or whatever the step is. You're providing a little snippet of code or a little lambda that's providing just the business logic that you want to do, and then the stream processor is responsible for distributing that and running that on the cluster. So it is a little bit of a different way of thinking. If you can get there, then it buys you a lot of scalability, but it's not the procedural step 1, step 2, step 3.
Understood. I have a question here from one of our attendees that I'd like to offer to you. So, Randy, why don't we start with you? Microservices promise scalability, but challenges may arrive. What are common scalability and performance challenges in microservices architectures, and how can organizations overcome them?
Okay. I'm afraid I'm going to sound like a broken record, but I think that one of the most common ones in my mind is basically synchronous interactions that cause you to kind of have a throughput ceiling, cause things to block, and cause you not to be able to use your CPU. So I think having a kind of a default asynchronous mindset is key, and will go a long way towards solving performance problems.
Jeremy, how about you?
Yeah, I'd agree with that general premise. Kind of on a higher level, I think there's things that you, as an organization, should really be opinionated about and draw like a golden path for, whether that's a technology that you adopt or how you want to approach security, how you want to approach being able to discover and call these microservices, to have some opinion there, because I think where a lot of microservice architectures can get very messy, and it's all with good intention, is kind of this empowered engineering team model where they might take a pod and say, choose whatever tools you like. And that can work well to empower teams, but it can get quite messy when all those things now need to interact with each other. And so I think there's a bit of opinionation and kind of like I'd say like golden path or standard to bring to the table there, just the right amount, so that teams can still feel free to express and you certainly don't want to create blockers, right? You don't want to create a security model where you're going to have to go through 6 layers of approval and all these different teams in order for a team to be productive. I think the empowered engineering team model is about giving the team the autonomy to be able to move quickly for what they need to do. But at the same time, if that decision makes it harder for teams to interact with each other, and that's just going to slow down the whole process. So it's kind of a Goldilocks principle in general of like, what's the right amount of kind of like standardization that we want in terms of technologies that we use, security model that we use, things like that. And then what are the things that we are, that we feel like we can loosen up or be a bit more liberal about so that teams don't feel like they have to go through like all of these crazy approval processes in order to get anything done.
Understood. We are at the top of the hour already, but before we go, real quick, one last question from me to you. Jeremy, why don't we start with you? If there's one thing you'd really like our attendees to walk away today keeping in mind, what would that be?
Yeah, I think for me, every time I give a talk about NATs, it's that I want people to walk away at least knowing that there's other options in how to build these things. That there's multiple communication strategies, multiple models, that there's technologies out there that allow you to express those different models. Quite often it's easy to reach for like the stuff that's just like off the shelf or like that's bog standard. But we're in a really interesting time as technologists and as software engineers where I think it's going to be critical that adaptability for an organization and for a team, that's going to be a critical component moving forward and staying advantaged in the marketplace. So I'd just encourage folks to play and to experiment. If you liked what you saw with NATs, go download it and play with it. It's meant to be played with. And so that's all I encourage folks to do is to kind of rethink and challenge their own assumptions about how a lot of these things traditionally work.
Great advice. And Randy?
Similar comment here. Just because the industry has kind of evolved certain categories doesn't mean that's all that exists. So have a look at technologies like Hazelcast and like NATs that combine a lot of the traditional, that cross some of the traditional categories and solve a lot of problems for you in one product and simplify your stack.
Well, I would like to give a huge thank you to our speakers today for coming on board and sharing their insights and expertise. Once again, Randy May, Principal Architect at Hazelcast, and Jeremy Saenz, Director of Developer Experience at Synadia. So if you in attendance would like to review this presentation or send it to a colleague, you can use the same exact URL that you used for today's live event. It'll be archived, and we will send you an email notification once that archive is up. And if you would like to grab a PDF of the deck, you can do that once the archive is up. You can go to the handout section on the console. Again, as I mentioned earlier, just for participating in today's event, you could win this $100 Amazon gift card. The winner will be announced on February 29th. We'll let you know by email if you're the lucky viewer. Thank you, everyone, for joining us today, and we hope to see you again soon.
Thank you.
Bye. Thank you.